Yeah, this is okay. Okay, hello everyone. Thank you for inviting me to the HICE seminar for University of Arizona. My name is Cheng-Han Hsieh. I'm this year's Hubble Sagan Fellow at University of Texas, Austin. So today I will show some of our work to trace the substructures in protoplanetary disk and try to pinpoint when planet formation begins.
Eugene, can you get rid of the top thing there?
Oh, can you see the
Oh
talk?
yeah, no, you're fine. There was a Zoom thing on this end. You're good.
Oh, I'm good. Okay.
Yeah, you're fine. Yeah.
Right. Okay. Just checking. You can hear and see my slide.
Yeah, you're good.
Okay. So one of the biggest problem in astronomy is to look for life outside Earth. Try to see answer questions such as are we alone in this universe and are any other Earth-like planets? So exoplanet is a rising field, and here shows like one of the beautiful artist's impression for the TRAPPIST-1 system. And this is a system located around like 40 parsec from Earth. So recently, with Kepler and TESS, we're starting to see discover many planets. So here shows like the sum of the planets distribution with their mass over their period. So until today, we have over 5,700 exoplanets discovered so far. So as you can see, these exoplanets, they occupy different mass period parameter space. You, and here shows like there's some hot Jupiters, uh, cold Jupiters, some sub-Neptune planets, and here also shows the position of our solar system planets. So there are a lot of unsolved mysteries in this field. For example, the famous photon gap, seeing the bimodality for sub-Neptune-sized planets with like super Earths and sub-Neptunes. And also there are different types of planets with different densities, radius, and mass. For example, like Earth-like planets, the rocky planet, Neptunian world, and also gas giants. And around in like 2011, people also discovered there's a um, Neptunian desert. So there seems to be a lack of sub-Neptune planets, hot Neptune planets. So this is still like a mystery, and it's possibly linked to the photo evaporation mechanisms in the disk. And interestingly, like one of the major discovery for the Kepler survey is to discover the peats in the pod pattern. So interestingly, that systems of like tightly packed inner planets appear to have like correlated sizes, masses, and their orbital spacing. So if you look at these Kepler discovered planets, they seem to be like evenly spaced and have like the similar size and mass. So uh, to explain these like planetary observations, it is important to take to study its formation. So I'm very interested in studying the protoplanetary disk, which is the environment forming these exoplanets. So I will focus two open questions. The first one is trying to look at protostellar disk and try to see when do protostellar disk substructures appear and to pinpoint the onset of planet formation. And the other question that I'll be into is the magnetic braking problem to see how do protostellar disk form. So just a quick introduction. So to trace the age of the protostellar system, we use the SED, spectral energy distribution. So early on, the whole system is very embedded. The protostellar cores are embedded in filament. So you see mostly like thermal dust emission. And over time, when these cores reaches mass greater than the Jeans mass, they will collapse and then form protostars with a disk in the center feeding by the materials like streamers. So in this class 0 stage, you'll start to see some of the scatter light from the protostar. And then over time, you can start to see the protostellar outflows widens and the density of the envelope decreases. So you see more infrared emissions from the disk. And then in flat spectrum sources, you start to see like the spectrum become flat between 1 and 10 micron. And this is due to the more infrared contribution from the disk. So we use the SED to trace the evolution of the protostellar system. So just a quick introduction. One value that we use is the bolometric temperature. So bolometric temperature is the temperature of the black body having the same mean frequency as the observed continuous spectrum. So early on, the emission is dominated by cold dust. And as it evolved, the protostellar system, you can start to see more infrared emission. So imagine you try to like overlay a black body curve on top of the SED, which gives you like a bolometric temperature. So as it evolves, as the protostellar system evolves, the bolometric temperature will increases over time. So this was proposed by Phil Mayers and Lada in 1993. They used the bolometric temperature to divide into different class 0, class 1, and class 2. Okay, so in the first part of my talk, I will talk about the giant planet formation time window, the onset of the planet formation problem. So there are two ways of forming a planet, two sets of models. The first set of models is the disk fragmentation. So you start with like a core collapse and then form like a very massive disk, and the massive disk will become unstable. And then the disk will start to fragment, and some of the surviving fragments will later form planets. So this is one way of forming planets. You form it top down. The other way to form planets is forming it bottom up. So you start with like a small dust grains, and these dust grains coagulate to forming larger pebbles. And these pebbles will later, due to like gravitational instabilities, such as streaming instabilities, and then will start to form like larger and larger planetesimals, and eventually the planet. So these class of models form the planets bottom up. So as reviewed by Dracoskoka et al. In 2023 in Planet 7 chapter, you start with like a small dust coagulate to meter-sized pebbles, and these meter-sized pebbles will quickly spiral inward towards the sun. This is known as the meter-sized barrier problem. So people come up with ideas such as streaming stabilities, having the pebbles get dust to gas ratio of 1, and then you can start to have like a streaming stabilities, and then quickly form larger planetesimals. And then planetesimals, you have like pebble accretion continue, and then once the central core reaches the isolation mass, then you have a runaway gas accretion, and this will eventually form a giant planet. So on the right-hand side shows some of like simulation results from Roman and 2020. This is just quickly illustrate how this works, like the dust coagulate, streaming instabilities, pebble accretion, then reaches the pebble isolation mass, and then quickly gas runaway accretion, and then form giant planet. So we can do this in simulations, But one of the big problems for planet formation is the lack of observational constraints. So you can run your sync particles and then build out like larger planet, but we don't really have observational constraint telling us at what time the dust should be like at which size and like how this process happens. There's a lack of timestamps for the planet formation process. So this is one of the bottleneck in the planet formation series. It's very important to study the substructures of the disk and try to find ways to constrain planet formation from observation. So just recently, ALMA starts to discover a lot of beautiful disk substructures. So here shows like a beautiful groundbreaking HL tau image. You probably have seen this before, like with a lot of beautiful rings and gaps. So this is the updated version by Eons et al. 2023. And from these rings and gaps, these are like a possible formation site for protoplanets with like the cluster of dust. So this is studying these substructures is very important. And however, there's some like questions, open-ended questions that hasn't been answered. Are these gaps formation site of a giant planet? If you look at the ALMA images, most of the rings and gaps are located very far away with much greater than 10 AU. But if you look at the California Legacy survey, the distribution of giant planet is usually located around like 3 AU. So there seems to be in conflict with each other. So maybe these rings and gaps are not really forming planets, are due to instabilities, or maybe this is like a hint for planet migration. So it is important to point out that all the previous studies predominantly target large, luminous, and more evolved disks with ages greater than 1 million year, class 2 disk. For example, like from the Odisha survey by Hsieh et al. In 2021, or the famous D-Shop survey led by Sean Andrews and his Harvard team in 2018. Recently, we start to have surveys looking at younger protoplanetary disk at class 0 and 1 stage. So this is the effort led by Ohashi in 2023, the eDisk ALMA large survey. So shown on the right-hand side. So from their samples of 20 class 01 sources, you can see that most of them are very smooth, very smooth. You don't really see substructures in them. So this is possibly suggesting that substructures in younger disks are very hard to find. So this poses like a lot of questions. Do substructures exist in the younger disk? Or like when do we start to see substructures? And it's important to point out, until today, we do not have a large, uniform, high angular resolution search for substructures for the youngest class 0, class 1 disk with age less than 1 million years old. So but studying these substructures in the youngest disk is very important because it tells us how early does the substructures form, and as a corollary, how early planet formation begins. So introducing our campus survey. So here are our campus team: me, Hector, Ashwarya, Jaime, Don, Maria Jose, Mike Dalham, and Diego. So we surveyed nearly all the embedded protostars in 7 nearby molecular clouds: Chamaeleon 1, Chamaeleon 2, Ophiuchus, Ophiuchus North, Aquila, Corona Australis, Serpens, from Dalham et al. 2015, which is the Spitzer Legacy survey, the core to disk survey, covering full class 0, class 1, and flat spectrum sources, and early class 2 sources with bolometric temperature less than 1900 Kelvin. So we use ALMA band 6. This is 1.3 millimeter, and with angular resolution of 0.1 arcsecond, which translates to 15 AU for 5 nearby clouds and around 40 AU for for Aquila and Serpens molecular cloud. So in total, we detected 184 disks. So here shows a comparison of our survey with other previous surveys. For example, the D-Sharp, ODSHA, and eDisk, all of them have much higher angular resolution, but their sample is very small and biased. So they usually pick the largest and brightest disk. So our campus survey, the angular resolution is around 15 AU, but we have 90 disks. And what is important about our sample is that this is a uniform sample. So with this uniform high angular resolution sample, we can start to conduct the statistical search for the protostellar disk substructures for the very first time. So here shows some of the substructures that we found in our survey. We aligned them by class 1, flat spectrum sources, and class 2. And from our survey, we found that disks with multiple ring systems morphology are generally much larger. So if you look at the one with the multiple rings, they are usually much larger than other types of morphology. And interestingly, our sample, we found there are two populations of these substructures in our sample. So one is like a C-type with like a donut type, which is a large central cavity, and the other one is centrally filled. And we see these two types of substructures very early on, in early class 1, all the way to class 2. And since this is ALMA band 6, 1.3 millimeter dust continuum, so the emission we're seeing are dust emission. It's not due to the free emission from the protostellar jet. So we don't know what is causing these morphology differences, and this raises a lot of interesting questions. For example, what kind of planetary systems will they evolve into, and which one will resembles our solar system? And interestingly, we found that multiple ring systems tend to be centrally filled. If you look at all the multiple ring systems, you don't see a large central cavity in these disks, almost without like exceptions. So all of these like multiple ring systems, they're always centrally filled. So this is a feature of multiple ring systems and possibly tied to its formation mechanism. So this is something that we don't know why, but this is something that should be investigated in the future. So to have like a uniform search of disk substructures, it's important to take into account of the effective angular resolution. As pointed out by Protostars and Planet 7, Bellero 2023, that majority of the disk without substructures have been observed at low effective angular resolution, with the diameter of the disk only sampled in 3 beams. So if you don't have enough sampling across the disk, you're not going to see substructures. So in order to have like a fair assess of the disk populations, we only analyze disk with diameter larger than 4 beams, meaning that you have at least 4 samplings across the disk diameter. And it is also important to take into account of inclination angle. If you have edge on disk, then you're not going to see substructures. So we exclude the edge on disk with inclination angle greater than 75 degrees. So here is our main result. So on the y-axis, plots the mass, disk mass, and radius. And the x-axis is the bolometric temperature, which is a tracer for the evolutionary stage. So the dashed line marks the boundary between class 0, class 1, and class 2 sources. So the time goes to the right, and the blue is this one with substructures, and the orange is without substructures. The black one are compact disks. They have diameter less than four beats. So one of the most important questions of our work is how early does these substructures form? So if you look at the plot, you can see that these substructures start to form at around 110 Kelvin. So this is around 0.1 to 0.2 million years. And another important question that we can ask is, when do most protostellar disks have substructures? So if we look at the data, you can see around 200 Kelvin, 210 Kelvin, that's the time when you start to see a lot of this substructure starts to pop up. So this translates to a time around 0.2 to 0.3 million years. So most of the protostellar disk starts to have substructures in early class 1. So this is much earlier than what is currently believed. Substructures appears much earlier on, and this shows that both the protostar and the protoplanet are forming and evolving at the same time. So we also look at the both the effective resolution as well as the linear resolution. So here is the same plot, but color coded by linear resolution. So the green shows the best angle linear resolution between 0 to 6 AU, blue 6 to 12, orange 12 to 18. So if you look at this plot, you can see in the very early phase, for the very young disk, most regardless of the linear resolution, there is no substructure detected. And later, if you focus on the green point, after 290 Kelvin, 14 out of 15 points have substructures. So this is telling us by around T-bar 290 Kelvin, which is around age of 0.2 to 0.3 million years, 94% of protostellar disks have 2 to 3 AU size substructures. So substructures in protostellar disk are not rare. Another important thing that to do is to look at the morphology. So from our data, we categorize the substructures into different types, such as spirals, multiple rings, ring with a central cavity, and embedded ring in disk. And on the right-hand side shows the plot of different substructure morphology as a function of bolometric temperature, which is a tracer for age. And from this plot, you can see that disk with multiple rings morphology are generally larger than the disk with a central cavity. So Hsieh et al. In 2019 proposed an evolutionary picture for disk substructures. So you start with like a very smooth disk without any gaps. And then later you start to see very shallow gaps, such as like multiple rings starts to form. And then over time, these dust will start to like accumulate into one of the inner rings adjacent to like a deep gap. So this will form like a bright embedded ring. And then over time, the dust will start to migrate inward, and the radial drift will cause the dust to dissipate. And eventually you will form with like a single ring with a huge central cavity. So if this picture is true, we should see the young multiple rings to be on the left, followed by the embedded ring in disk, and then the ring with a central cavity should populate on the right, being the most evolved systems. But that's not what we're seeing with our data. And instead, we see like different morphology spread out across different age. So instead of like a single evolutionary sequence, what we're seeing suggests there are different populations of substructures, possibly originated from different mechanisms. It's important to point out that the sample is only complete for 0.01 solar mass. We for the compact disk, we do not really know whether they have substructures or not. So that is something that we will investigate further. So another important consideration for the onset of the substructures is the optical depth effect. It is possible that early on, due to the higher mass and higher temperature, the disk might be optically thick. So the transition from substructures, no substructures to substructures might be due to the optical depth effect. So to test this, we estimate the brightness of temperature of the disk using the full Planck equation and compare to the dust equation. And we do not see a sharp transition of the ratio, which gives you the tau, the optical depth, at the boundary between substructure and no substructures. So this is suggesting that the onset of substructure that we're seeing is not completely due to optical depth. So another thing that we done is we also look at the protostellar disk substructure detection rate. So we separate the samples by both class and linear resolution. So class 1 and flat with bolometric temperature greater than 110 Kelvin, which is after the onset of these substructures, and also class 2. So what is interesting is that we found that the class 1 and flat substructures detection rate is comparable with the class 2 substructure detection rate. So this is telling us that if you take into account of all the observational bias, protostellar disk substructures are not rare. The class 1 substructure detection rate is comparable with what we're seeing in class 2. So this means that most of the substructures are developed very rapidly early on between class 0 and early class 1. So the finding of substructures developed very early on in early class 1 has a lot of implications. In addition to like the onset of planet formation, it is a possible solution for the CAI storage problem in our solar system. So the CAI storage problem of meteorites is a well-known problem for the solar system community. So the problem is this. The calcium, aluminum, titanium formed near the sun with temperature around like 1,400 Kelvin. They have like size around 0.1 millimeter to 1 centimeter. They should all spiral in towards the sun. However, CAIs are found in meteorites. Not only they're found in meteorites, they are found in meteorites far away from the sun, in carbonate chondrites. So this is very puzzling. Why are we seeing these CAIs in carbonate chondrites? So one possible solution proposed by Stephen Dash in 2018 is you have early formation of Jupiter. You have Jupiter's 30 Earth mass core formed at around 3 AU, around 0.6 million years, and this opens up a gap. So if the CAI are within the 3 AU, all of them will radially drift and get accreted onto the sun. But any CAI outside of Jupiter's orbit, they can remain in orbit and then being captured and incorporated into carbonous chondrites. In addition to the CAI problem, another in addition to the ALMA substructures, we can ask like, are there other observational time constraints for the giant planet formation? So we can also constrain the planet formation from our sun, from the solar neutrino flux. So this is known as the solar modeling problem. This is a well-known problem in the solar physics community. So the problem is this: our sun has a very metal-rich core, but a very low metallicity surface. So the question is, how can we explain this metallicity difference in our sun? The current solar evolutionary models are unable to reproduce both the spectroscopic, helioseismic, and also neutrino constraints consistently. So one of the solutions proposed by Kimi Tomo in 2022 is that the solar metallicity structure corresponds to other imprints of the planet formation. So early on, you have a lot of like metals, I mean like dust. You have a lot of dust are freely accreted onto the central protostar, our sun. So this helps build up like a metal-rich core. And once the protoplanet starts to form, they will curve out gaps and then prevent the dust from drift inward. So when the planet starts to form, then the metallicity accreted onto the sun drops. So this will later form a low metallicity surface. So from their simulations, they found that planet formation process leading to the metal poor accretion of the last 4% of young sun's total mass. So this is around 2.2 million years. So we have like constraints to look at the time window for planet formation. We have constraints from our ALMA observations, looking at when the substructure starts to appear. That gives us like a start time. And we can also look at the solar structures and look at the metallicity, the neutrinos and spectroscopic helioseismic data for our sun, and then try to explain the metallicity gradient inside the sun. This gives us like the time window when like planet formation are complete and when dust are blocked from accreting onto our sun. In addition, we can also look at meteorites, look at CAIs, which gives us another time constraint on when the substructure should form in our solar system. So here are our conclusions. So we conducted the first statistical search for substructures in the youngest class 01 disk. And we found that these substructures start to appear in sources with bolometric temperature greater than 110 Kelvin, which is around 0.1 to 0.2 million years. This is way younger than the current planet formation models. And this is very surprising. And this is during the phase when the central protostar is still accreting materials and is still building up its mass. So this suggests that both the planet formation and the star formations occurs at the same time. And they form at the same time and also evolve together. And in addition, we find like multiple rings morphology are generally larger than disk with a central cavity. And from our data, we found there are two types of substructures. One type is the one with a central cavity like a donut shape. The other one is like a egg shape, which is centrally filled. And multiple ring systems tend to be centrally filled. We don't know what is causing these substructures, and we don't know what these what kind of planetary system textures will they evolve into, and which one resembles our solar system. There are still a lot of open-ended questions that needs to be answered, and with more data on planets and also disk, in the future will be interesting to connect the disk morphologies and initial conditions with the Kepler and TASS exoplanet demographics. So this is a very exciting field, and thank you for inviting me to share some of my results. And I will leave out my conclusion slide and take questions. Thank you.
Any questions?
Yeah, so thanks for the really nice talk. I have a couple of questions. So you mentioned that this is a complete survey. Um, how are you defining like the completeness, or like how are you sort of quantifying that?
So we observe nearly all the sources in 7 nearby molecular clouds from the Dahan et al. 2015 catalog. So this is from is nearly complete, nearly complete. So Daham's catalog is the Spitzer Legacy Survey. It's called the Core 2 Disk Survey. So they have like a sample of more than 2,000 YSOs. And a lot of them are class 2 and class 3. So we look at all the members in these 7 nearby molecular clouds, and we use ALMA to target nearly all the embedded protostars in this in the catalog. So it's nearly complete.
Okay.
There are other molecular clouds that have more protostars, but they are located further away. So all of these are within 200 parsec. Like for the one that I show in the plot. So if you go beyond 200 parsec, then you need much higher angle resolution to reach the 15 AU linear resolution, and this will easily triple, even like be 10 times more ALMA time. So this is pretty complete for these 7 molecular clouds.
Okay. And then your resolution, I was curious about. So in your images, we can kind of see, is the resolution, yeah, so for example, in this image here, if I just pick, for example, the fourth source on the first row, uh, the width of that thing, it looks to be tens of AUs. Is that correct? What is and the beam size, is that your resolution element there?
Yeah, the beam size is my resolution element, and that's
Okay.
around 15 AU.
So are you you're effectively sensitive to these Jupiter type farther away planet formation rings.
Yeah.
And so like on the science side, like these, so are you saying like that you don't see any evidence of evolution from one structure to another based on sort of time scales? Is that accurate?
So because we're seeing like the morphology um at or at different across different evolutionary stages, so it's very hard to pinpoint how the morphology evolved. And if you look at the plot that I showed, I think this one,
Mhm.
see like for example multiple rings. You see them in class 1, you see them in class 2. And you look at like ring with a large central cavity, they are also very spread out across different evolutionary stages. You don't it's not really conclusive right now, but you cannot you can see that these are very spread out. So it's possible instead of like a single evolutionary picture proposed by Hsieh et al. 2019, it is more likely that there are many
For different
different populations.
scenario for
Yeah, different mechanisms can generate substructures. For example, instability can generate substructures. Exoplanet, protoplanet can generate substructures. And it could be there until today, there are more than 20 mechanisms that can generate substructures. So it's still like a very hard question and haven't been answered is like what is the origin for the substructures? But even if these are not generated by planets, the formation of substructures are the ideal site for forming planets. The highly concentrated dust rings, these are favorable sites for planet formation, and they can quickly speed up planet formation at these like regions.
have you checked the property of the central star? I mean, is there difference for their central star?
That's a good question. We don't really know. First of all, these are like young sources. They are very embedded, so you
Oh
don't
yeah, that makes
know,
sense.
cannot really see like the optical images for these stars. And also we don't really know the mass of the central protostar at the moment because it's very tricky to get the mass of the protostar. You need to line data to model disk rotation to get a central mass. So we don't have the mass of the central star as well.
Okay.
So if these are like class 0, 1, and 2 between the three of them, if you went and looked with JWST sort of MIRI kind of wavelength range, that's where you would start to see your starlight and reflected light dominate. Like, do you suspect you could, like, if you looked at
Radio,
the, huh?
it's radio wavelength, so it's mostly the thermal emission.
Well, for MIRI, yes. I think
Yeah.
if you use MIRI, you can see the central protostar. Yes.
Okay, yeah, that might help clear things up. I don't know if there's plans to observe with MIRI.
Not yet at the moment. In the future, I'm interested in do JWST follow-up.
Okay,
I mean, after a year or two, after I have like this paper published and have, yeah, it
yeah,
will be interesting to do JWST follow-up, especially on these selected protostellar disk with substructures.
yeah, it would be really interesting to see if you even see the same substructure, and then like if the star light tells you something about different substructures.
Yeah, I don't know maybe there's some correlation with the stellar properties.
Mhm.
That's something that haven't been explored. A lot of open
Because
questions.
yeah, if here you're looking at the same band, you're just sampling one portion of the SED, right? So if your SED is doing something different in the sort of stellar part of it, which is the sort of 1 to 10 micron region where starlight would dominate, that's where you might spot that. But it would be harder to say with ALMA.
Yes, this
Yeah,
is only one wavelength,
yeah,
1.3 millimeter. In the future, it will definitely be interesting to do the same study but at different wavelengths.
yeah. No, these images are really beautiful though. Like they're
Here,
fantastic images.
a couple of years to reduce the data.
Yeah, I can imagine.
I started working on them in 2021.
I also see like all the null detections, which like I can imagine you have to reduce those two, and yeah,
Yeah, I have
no,
to use like 108.
yeah, this is a lot of data.
Like it's like very just take time. Just like
Yeah,
do one reduction and then do self-calibration for ALMA like one by one by like eventually it'll complete. But it's I think it's definitely worth it. It's
Oh yeah, for sure. Yeah, I don't think I have any more questions.
Yeah, for me, I'm really interesting, as I said, interesting about the wavelength, not wavelength, the size of the grand distribution, the grand size distribution. But I understand you were not able to obey from single wavelengths. Yeah,
yes, the way the grain size distribution is also something that's interesting, but we don't have any other wavelength data. This is
it's
the
literally really important for the scenario. I mean, the formation scenario.
yes. So in the future, maybe in the long distant future, we'll start to look at different wavelengths and then try to recreate the same plot, but with different band.
Yeah.
Wavelengths.
And actually, there's another difficulty when even you have several wavelengths observation, it's still really hard to find a those distribution, those grand size distribution. Yeah, the model is not how to say level degeneracy.
Yes.
Yeah. Any question from online? There are two attendants online. Oh, one disappeared.
Hmm.
If not, let's send Cheng-Han again.
Okay, thank you for inviting me. Can you remind me what's your name?
日家.
Oh, I mean like I know you. I mean like the
Oh,
audience.
Sanchit?
Sanchen.
Yeah.
Sanchen.
And I'm just Stephanie.
Stephanie. Oh, nice to meet you all. I will I'm thinking about visiting UA maybe next year, sometime next year.
Okay.
Yeah.
Yeah. Are you interested about instrument part? I have to ask that.
Yeah, maybe depending on the time. Okay, thank you for inviting me. Yeah.